The water is brown and moving and full of teeth, and 1.5 million hooves are about to decide all at once that today is the day. You can hear it before you see it, a sound like distant thunder that never stops rolling. Dust rises off the riverbank in a gold haze. Somewhere in that haze, a single wildebeest takes one step toward the water, then another. Then, without any signal you can point to, without an announcement, without a single individual in charge, the entire front line surges forward together, like the bank itself exhaled. I was standing exactly where I shouldn't have been standing. I remember thinking, this is the best seat in the world. I remember thinking that for about 4 seconds. Then 4 seconds became a very bad decision, and a very bad decision became several thousand pounds of panicked mammal deciding collectively, without malice, without leadership, without a single wildebeest ever looking me in the eye and going, let's get him, that the riverbank I was standing on was now part of the crossing. Yep, that's me. You're probably wondering how I ended up here. Oh, hey there. I've been dead a while now. Long enough that I've stopped counting in years and started counting in migrations. Long enough that I've watched this exact river crossing happen so many times I could narrate it in my sleep if I slept, which, fun fact, I don't, because being dead comes with excellent free time and absolutely no circadian rhythm. And somewhere around migration number, 400, I stopped being angry about how I died and started being fascinated by it. Because here's the thing nobody tells you about a wildebeest crossing or a starling murmuration or a beehive deciding where to live next. There is no wildebeest in charge. There was no general standing on a rock barking orders. There was no meeting. There was no memo. 1 million animals moved as one single fluid, terrifyingly coordinated organism, and not one of them was steering. That idea followed me into the afterlife and never really let go. So that's what we're doing today. We're taking apart the machine. We're figuring out how herds, flocks, schools, and swarms pull off something that should be impossible, perfect group coordination with zero leadership, and why evolution apparently looked at everybody just follow some simple rules and hope for the best and said, yeah, that'll work great. Here's the assumption almost everyone walks around with. Somewhere in that stampede, that flock, that swarm, there's a boss, a lead goose, an alpha wildebeest, a general calling the shots while everyone else falls in line like a nature documentary version of a corporate org chart. It's wrong. Not slightly oversimplified wrong, structurally, fundamentally wrong for the vast majority of these systems. What actually happens is something scientists call self-organization, and it is, without exaggeration, one of the strangest and most elegant tricks biology has ever pulled off. Self-organization means complex group behavior emerges from simple individual rules, with no blueprint and no boss. Every wildebeest isn't reading the herd's mind. Every wildebeest is reading its neighbors, usually just a handful of them, and reacting in real time. Multiply that by 100,000 individuals doing the same tiny calculations simultaneously, and you get something that looks from a distance like a single terrifying superorganism with a plan. It doesn't have a plan. It has math, which honestly might be scarier. Think about traffic for a second. Nobody's directing every car on the freeway. There's no traffic god watching from above adjusting lanes. And yet you get waves, that mysterious phantom slowdown for no reason that ripples backward through hundreds of cars. That's not caused by an accident. That's caused by one driver tapping their brakes and everyone behind them overreacting, in sequence, like dominoes made of Toyotas. Herds do the same thing, except when a wildebeest overreacts, it's not tapping the brakes, it's triggering a stampede that ends careers. Mine, specifically. Fast Facts 1. A starling flock can involve upwards of 100,000 birds turning in unison within a fraction of a second, faster than any single bird could consciously process a group decision. Locust swarms have been recorded stretching over 1,000 square kilometers, containing tens of billions of individuals, and every single one of them is only paying attention to the neighbors immediately around it. Fish schools can compress and expand density in less time than a predator's brain can lock on to a single target, which, spoiler, is the entire point. None of this required a leader. It required rules. Which brings us to something even stranger, the accidental discovery that changed how scientists think about all of this forever. In 1986, a computer graphics researcher named Craig Reynolds wasn't trying to solve a biology problem. He was trying to make flocking birds look convincing in animation because at the time, every digital flock looked like a glitching cloud of confused pigeons. So he built a simulation. He called the simulated creatures boids. birdoid objects because scientists are only funny by accident, and he gave each boid exactly 3 rules. Rule 1, don't crash into your neighbors. Rule 2, generally match the direction and speed of the birds around you. Rule 3, try to stay near the group, don't wander off alone. That's it. 3 rules. No lead boid, no master plan, no boid appointed team captain. He ran the simulation, and what came out the other side was flocking behavior so realistic that biologists studying actual living birds started using his model to explain what they were seeing in the field. Let that sink in for a second. A guy trying to make a video game look nice accidentally reverse-engineered one of nature's oldest survival strategies. Evolution spent millions of years perfecting a system, and a computer scientist stumbled onto the cheat codes in an afternoon.
This is less master strategist coordinating a species and more tiny caffeinated accountant managing 3 simple rules at incredible speed. Every wildebeest, every starling, every anchovy is running some biological version of Reynolds code. Don't crash, match your neighbors, don't get left behind. Nobody's in charge because nobody needs to be. The system runs itself. Which is exactly why when I stepped onto that riverbank, nothing was going to negotiate with me. There was no wildebeest CEO I could have reasoned with. There was just momentum multiplied by 100,000 nervous systems all obeying the same 3 rules at once. You're standing at the edge of a river crossing. The air smells like dust and adrenaline. You feel it before you hear it, a vibration traveling up through the ground and into your knees. You look left. A wall of bodies wide as the horizon is already moving. Here's the part your brain refuses to accept in the moment. There is no individual decision maker to appeal to. You can't make eye contact with the one who's in charge because there isn't one. You are not facing an animal. You are facing a fluid made of muscle and horn and momentum, governed by the same simple rules Reynolds coded into his boids. Stay close, don't collide, match your neighbors. You take 1 step backward. It doesn't matter. The front line has already made its decision 3 seconds ago, and the decision is not about you. I want to be clear, the wildebeest weren't wrong. They were following instincts forged over millions of years, specifically to move huge groups safely across dangerous terrain. I was the anomaly in the system. I was the bug in otherwise flawless code. Which brings us to something even weirder, the birds that turn as one and how scientists finally figured out how they're actually doing it. For decades, the leading theory about starling murmurations, those massive swirling black clouds of thousands of birds folding and twisting across the sky like liquid smoke, was that each bird was tracking every other bird in the flock, which mathematically is an absurd amount of processing for a brain the size of a peanut. Then, in the mid-2000s, a team of Italian physicists led by Andrea Cavagna and Michela Ballerini did something nobody had really pulled off before. They photographed massive starling flocks over Rome from multiple angles simultaneously and used the images to reconstruct the 3-dimensional position of every single bird, then tracked how each one moved relative to its neighbors. What they found rewrote the textbook. Each starling isn't tracking every bird in the flock. Each starling is only paying close attention to about 7 or 8 neighbors, regardless of how close or far away those neighbors physically are. Scientists call this topological distance instead of metric distance. Translation, a starling isn't asking who's within 10 feet of me. It's asking who are my closest 7 friends wherever they happen to be standing. Why does that matter? Because it means the flock stays coherent even when it stretches, compresses, or gets attacked from one side. If every bird only cared about physical distance, the flock would shatter the moment it got dense in one spot and thin in another. By tracking a fixed number of neighbors instead of a fixed distance, the whole formation stays glued together no matter how it deforms. It's the difference between a rope and a chain. Pull on a rope and it stretches unevenly. Pull on a chain and every link stays connected to the ones next to it. What is actually going through its head? Here's where we have to be honest about what's known versus what's hypothesized. Scientists know with strong observational evidence that starlings track a small fixed number of neighbors rather than all birds in a radius. What's still debated, genuinely actively debated in ongoing research, is exactly how a starling's visual system processes 7 moving targets simultaneously and converts that into a split-second flight adjustment.
The leading hypothesis involves something researchers call scale-free correlation. Essentially, when one bird changes direction, that information doesn't just affect its 7 neighbors, it ripples outward through the whole flock, bird to bird to bird, faster than sound travels. In some measurements, a directional change has been clocked propagating through a flock at speeds suggesting each bird reacts in well under 1/10 of a second. That's not a bird thinking, that's a bird's nervous system doing something closer to a reflex, tuned by evolution to treat "my 7 neighbors just twitched" as an instruction with the same urgency as touching a hot stove. Nobody's found the neural wiring diagram for this yet. It's likely, not confirmed, that specialized visual processing regions handle this at a near instinctive level. Otherwise, the starlings isn't choosing to turn, the turning is choosing it. The myth is somewhere in a murmuration there's a lead bird everyone else is following, like a general directing troop movements from the front. The verdict? False. Completely, thoroughly false. Here's why it's false. Researchers have tracked murmurations extensively enough to confirm that direction changes can literally originate from any bird, anywhere in the flock, front, back, middle, edge. There is no permanent leader position. What looks like following the leader is actually thousands of birds simultaneously reacting to their own local neighbors in a chain reaction that happens to look from a mile away like it's being conducted by someone. It's the same illusion as the wave at a stadium. Nobody's in charge of the wave. One section stands up, the next section reacts, and from the blimp camera, it looks like a single coordinated event. Up close, it's just a few thousand people responding to the people directly next to them, half a second apart.
Which brings us to something even stranger than birds, because at least birds are all trying to do the same thing. Bees have to agree on something that actually matters, where they're all going to live for the rest of their lives. When a honeybee colony outgrows its hive, roughly half the colony, tens of thousands of bees, leaves with the old queen and clusters together in a temporary swarm, usually hanging off a tree branch like a furious buzzing beard. And then this swarm has to make one of the most important decisions of its collective life. Where's the new home going to be? There's no queen making this call. The queen, frankly, doesn't get a vote. This entire process is run by a few hundred scout bees, and the way biologist Thomas Seeley spent decades documenting it reads less like animal behavior and more like an actual functioning democracy, one that uncomfortably runs better than most human town halls. Scouts fly out independently, searching for potential nest sites, hollow trees, wall cavities, whatever real estate is available. Each scout that finds a promising site flies back and performs a waggle dance, a figure-8 motion that encodes both the direction and distance of the site, danced with an intensity roughly proportional to how good the location actually is. Better site, more enthusiastic dance. Worse site, weaker, shorter dance. Other scouts watch these dances, and, this is the key part, some of them fly out to check the advertised site for themselves. If they agree it's promising, they come back and dance for it too, adding their vote. If they don't like it, they simply stop dancing for their own site and go check out someone else's. Over hours or days, support gradually consolidates around the best options, and weaker options quietly lose their dancers. Fast fact 2. Seeley's research found that scout bees will actually dance more vigorously for a superior site even after already committing to a decent one, meaning the swarm keeps auditioning better options even mid-decision. A swarm typically evaluates somewhere between 10 and 20 potential nest sites before settling, and studies have found the group tends to pick the objectively best option among them at a strikingly high rate, not because any bee compared all the options, but because the loudest, most repeated dances mathematically tend to belong to the best real estate. The final decision point is triggered by something called quorum sensing, when enough scouts, often somewhere around a few dozen, are simultaneously present at the same site at once. That site gets locked in, and the scouts return to trigger the rest of the swarm to take flight toward it. Myth: the queen bee is the decision maker. She's the queen, right? Royalty, in charge, calling the shots. The verdict? False, and honestly kind of insulting to how much unpaid labor the scout bees are doing. The queen's job during this entire process is to survive being repeatedly poked and prodded by her own daughters until she's herded into flight toward wherever the scouts have already decided to go. She has zero input on site selection. She is essentially cargo with excellent PR. The real system is a distributed vote among scouts weighted by dance intensity resolved through quorum sensing, a total head count
count trigger, not a royal decree. If you wanted a human comparison, it's less the queen has spoken and more enough people liked the same restaurant on the group chat that we're all just going. Which brings us to land mammals, who, it turns out, vote too, just with slightly less dancing and slightly more standing around looking annoyed. Red deer do something that when researchers Larissa Conrad and Tim Roper first documented it properly, forced a lot of scientists to rethink what group decision-making even meant outside of humans and bees. Red deer herds need to decide collectively when to move from resting to grazing. There's no dominant deer announcing, "All right, everyone, up." Instead, individual deer simply stand up when they personally feel ready to move. As more deer stand, the probability that the rest of the herd follows increases. And Conrad and Roper's modeling found that herds behave as though they're using something close to a majority rules threshold. Once roughly enough of the herd is standing, the whole group transitions together, almost like the herd is running an informal biological election with body posture as the ballot. African buffalo do something even stranger. Researchers observing buffalo herds noticed that individuals will stand up, stare in a particular direction for a period, then lie back down, seemingly doing nothing. But when researchers tracked the direction these standing, staring buffalo were facing, they found it strongly predicted which direction the herd eventually moved. And the direction that got the most votes, the most individuals staring that way, tended to win. No vocalization, no physical herding, just quiet, repeated directional staring, tallied by the group like a silent ballot box nobody admits exists. Imagine you're a red deer. It's mid-morning, you've been lying in the grass for an hour, and you're getting restless. You don't know if anyone else is ready to move. There's no signal being given, no dominant stag barking commands, so you do the only thing available to you. You simply stand up. That's your entire vote. You're not leading anyone, you're not asking anyone to follow, you're simply expressing your own individual readiness and trusting, although trusting implies a level of conscious awareness we can't actually confirm, that enough others feel the same way, the herd will tip. 10 minutes pass. A few more deer stand. Then, a few more. There's no announcement when the threshold is crossed. There's just a moment where enough of the herd is upright that the group as a whole begins to drift toward the grazing ground. And the deer that were still lying down get up too, because staying down alone is a worse option than standing has ever been. That's the entire mechanism. No leader required, just quiet individual signals accumulating until they cross an invisible line.
Let's ground this in actual numbers, because the herd decided sounds mystical until you see the math behind it. Conrad and Roper's mathematical models comparing despotic leadership, one dominant animal deciding for everyone, against shared democratic decision-making found something counterintuitive. Shared decisions, on average, tend to be more accurate for the group as a whole and cost the group less energy overall, even though they take slightly longer to reach. Think of it like the difference between one manager making a snap call that might be wrong versus a team quietly voting, slower but more often right, because errors get averaged out across many individual judgments instead of riding entirely on one animal's mood that day. To put swarm scale into perspective, locust swarms during severe outbreaks have been estimated to include tens of billions of individual insects, and a single large swarm can consume in one day roughly the same amount of vegetation that tens of thousands of people would eat in that same day, a genuinely staggering number for a creature that individually weighs about as much as a paperclip. Multiply a paperclip's appetite by a number too large to comfortably picture, and you get famine-level agricultural damage across entire regions, historically documented as far back as ancient Egypt. And that giant appetite brings us to the darkest part of this whole story, because sometimes this beautiful decentralized system doesn't produce something majestic like a murmuration. Sometimes it produces something apocalyptic. Locusts, for most of their lives, are not locusts. They're grasshoppers, solitary, relatively harmless, minding their own six-legged business, actively avoiding each other. Then, under the right conditions, usually drought followed by sudden rain which crowds them into shrinking patches of surviving vegetation, something switches on. Physical contact between individuals, specifically repeated touching along the hind legs, triggers a surge of serotonin in their nervous system. This is documented, replicated research, led significantly by entomologist Steve Simpson and colleagues. That serotonin surge doesn't just change behavior, it changes the insect's body. Color shifts, metabolism shifts, and critically, their instinct flips from avoidance to attraction. They start actively seeking out other grasshoppers instead of avoiding them. This is the transformation from the solitary phase to the gregarious phase, and it's one of the only known cases in the animal kingdom where a single neurotransmitter, triggered by simple physical touch, can flip an organism's entire personality and turn a shy loner into a card-carrying member of a billion-strong doomsday swarm. Here's the part that should really bother you. Once enough grasshoppers are packed together and gregarious, they start actively marching towards each other rather than away, which packs them even tighter, which triggers more serotonin, which recruits more individuals. It's the exact same positive feedback loop that made the honeybee scouts converge on the best nest site, except instead of finding a nice hollow tree, it ends in an unstoppable wall of insects eating an entire province's harvest. Same mechanism. Democracy and disaster running on identical code. Myth number 6. Swarms, stampedes, and mass animal movements are chaotic, panicked, out-of-control events with no internal logic. The verdict? False. And this one matters because it's the exact myth that got me trampled. From a distance or from directly underfoot, which I do not recommend, it looks like pure chaos. Up close, mathematically, it's the opposite of chaos. It's one of the most efficient information processing systems biology has ever produced. Every individual is running simple, consistent rules reacting to real information from real neighbors in real time. The system isn't out of control. The system is control, just distributed across thousands of nervous systems instead of concentrated in one. What feels like panic to a human standing in the middle of it, to the herd, is closer to an extremely fast, extremely quiet vote. I just happen to be standing in the polling place. Now, before you assume every collective animal behavior on Earth is leaderless, I have to be honest with you, because scientific honesty is the whole deal. Some species genuinely do have leaders, and it would be dishonest to pretend otherwise just because it ruins a clean narrative. Elephant herds are matriarchal, and the matriarch, usually the oldest, most experienced female, genuinely does make key decisions, particularly about where to find water during drought based on decades of accumulated memory. Researchers studying elephant herds have found that herds led by older matriarchs respond more effectively to drought conditions, likely because that matriarch has personally lived through more previous droughts and remembers where the water was decades earlier. That's not distributed decision-making. That's institutional knowledge stored in a single individual, and it can be the difference between a herd surviving a drought or not. Sperm whales operate in tight matrilineal family units, and evidence suggests older females play an outsized role in decisions about defense and movement, particularly when younger calves are threatened by predators like orcas. So the honest answer is, it's not one system. Nature runs both models, leaderless swarm democracy and matriarch-led institutional memory, depending on what the species actually needs. Herds facing simple, fast, repetitive decisions, like which way do we all turn right now, tend to favor the decentralized system because it's fast and averages out individual error. Herds facing complex, rare, high-stakes decisions, like where is the water during the worst drought in 50 years, tend to favor concentrated experience in one knowledgeable elder. It's the difference between reflex and wisdom, and evolution apparently decided both have their place. Here's an idea that's going to mildly ruin the wholesome group unity vibe we've had going, and honestly, I think that's healthy, because nature doesn't run on wholesome vibes. It runs on math and self-interest. In 1971, biologist William Hamilton proposed something called the selfish herd theory, and the core idea is almost uncomfortably cynical. Animals don't group together primarily out of cooperation or altruism. They group together because being surrounded by other animals reduces their individual odds of being the one a predator catches.
Picture a group of fish as a crowd of people trying not to be the person a mugger picks. You don't need to be faster than the mugger, you just need to not be the person standing at the edge of the crowd. Hamilton's math showed that if every individual animal simply tries to put other animals between itself and the danger, the natural result, with zero cooperative intent whatsoever, is a tightly packed group. Nobody's trying to protect the herd, everybody's trying to hide behind everybody else, and the herd is the accidental byproduct. This connects directly to something called the predator confusion effect, which has actual experimental support. Studies using computer-simulated predators attacking simulated prey groups found that predators had measurably lower capture success rates against larger, denser, more synchronized groups, likely because rapid, unpredictable group movement overwhelms a predator's ability to visually lock on to one single target, an effect called target switching or attentional overload.
So the beautiful swirling murmuration you see in the sky dodging a peregrine falcon in real time isn't a heroic collective defense strategy. It's 10,000 individual birds, each one just trying not to be the one the falcon locks onto. And the swirling shape is the accidental art produced by 10,000 acts of pure self-preservation happening at once. Evolution looked at everyone selfishly hides behind everyone else and somehow turned it into one of the most visually stunning phenomena in the natural world. That's either deeply poetic or deeply depressing. I've had a long time to think about it, and I still haven't decided. Fast Fact 3. Sardine bait balls, those massive spinning spheres of fish you've probably seen in documentary footage, form specifically because individual sardines are simultaneously trying to stay central to the group, and the spinning, whirling shape is the mathematical result of thousands of fish, each independently avoiding the outer edge. Zebra stripes are hypothesized, among several competing theories, to help disrupt a predator's ability to visually isolate a single individual from a moving herd, similar to the confusion effect seen in fish and birds, though this remains an area of active scientific debate, not settled fact. Musk oxen form a defensive circle facing outward when threatened by wolves, horns pointed towards the danger, one of the few herd formations that genuinely does function as a coordinated defense rather than purely selfish positioning, likely because musk oxen calves, positioned safely in the center, benefit the whole group's genetic future. Which brings us to the last piece of this puzzle, because so far we've talked about animals watching each other, but some species don't even need to watch, they just leave messages. Ants don't have a group chat. They don't have a queen barking orders. Despite what her title implies, she's mostly just an egg-laying machine with zero managerial authority over foraging decisions. And yet, ant colonies solve incredibly complex logistics problems, like finding the shortest path between a food source and the nest, without any individual ant knowing the whole map. The mechanism is called stigmergy. And it's genuinely one of my favorite concepts in all of biology, dead guy opinion, because it means the ants aren't really talking to each other at all. They're talking to the environment and letting the environment talk back. Here's how it works. An ant leaves the nest and wanders somewhat randomly until it finds food. On the way back, it lays down a trail of pheromone. Other ants encountering that trail are more likely to follow it than to wander randomly themselves. If they reach food by following it, they reinforce the trail with their own pheromone on the way back. Shorter paths get walked more times per minute, simply because there's less distance to cover, which means shorter paths accumulate pheromone faster, which makes them more attractive to the next ant, which reinforces them further. Longer, less efficient paths, meanwhile, get walked less often, and pheromone naturally evaporates over time, so weak trails fade into irrelevance. Nobody calculated the shortest path. Nobody compared routes. The colony didn't solve a math problem. The math problem solved itself through simple positive feedback, the exact same core mechanism that let honeybee scouts converge on the best hive site and let locusts converge into a devastating swarm. Same equation, wildly different outcomes, depending entirely on what's being reinforced. Myth. Ants communicate through some kind of sophisticated, almost language-like system, coordinating complex plans the way a military unit would. The verdict is false, in the sense that matters. There's no ant HQ drawing up battle plans on a chalkboard. What looks like sophisticated coordinated strategy from the outside is actually a huge number of extremely simple individual ants, each one just reacting to pheromone concentration in their immediate surroundings, with zero awareness of the larger pattern they're collectively creating. This is stigmergy's real magic trick. Genuinely complex, adaptive, borderline intelligent-looking group behavior built entirely out of individually stupid components. None of the parts are smart. The system is smart. It's the biological version of how a single brain cell doesn't know Shakespeare, but 86 billion of them stacked together somehow produced Hamlet. So why does any of this exist? Why did evolution favor distributed dumb rules over one smart leader across so many species, so many times, independently in fish and birds and insects and mammals that haven't shared a common ancestor in hundreds of millions of years? Because leaderless systems are absurdly cheap and absurdly fast, and in the wild, cheap and fast beats smart and slow almost every single time. A centralized leader is a single point of failure. Remove that one individual through predation, injury, or old age, and the whole system can collapse. A decentralized system has no single point of failure because the intelligence isn't stored in any one animal. It's stored in the relationships between all of them, which means you can remove huge numbers of individuals and the basic behavior still functions.
It's also blisteringly fast because no individual has to wait for permission. A starling doesn't wait for the flock's approval to dodge a hawk. A red deer doesn't wait for a vote to be tallied before standing up. The decision-making and the acting happen at the same time, distributed across every single member simultaneously, which is exactly why a 100,000-bird flock can change direction faster than a single human eye can track it. You thought you'd outsmart a system that's been running unsupervised for millions of years with zero management overhead. Spoiler, you were wrong. I certainly was. Being dead has given me a lot of free time to reflect on the specific ways I personally misunderstood the natural world right up until the natural world corrected me, permanently. So here's what I've got, for whatever it's worth to someone still running on a heartbeat. 1. There is no leader to negotiate with in a stampede, a swarm, or a crossing. You are not dealing with a decision maker. You are dealing with a distributed system reacting to local information. Do not attempt eye contact with the one in charge. There isn't one. 2. If a large group of animals is moving, respect the momentum, not the intention. The herd doesn't hate you. The herd doesn't know you exist as an individual. That's somehow worse. 3. Give wide, unpredictable feeling group movements far more space than feels necessary, because the confusion effect and predator avoidance instincts that make these animals hard for predators to target also make them hard for you to read. 4. If you're observing a river crossing, migration, or large herd movement, elevate yourself. Literally, physically get higher ground rather than positioning yourself at the same level as the animals. I cannot stress this one enough, for reasons that are at this point extremely personal. 5. Remember that quiet, still-looking animals, standing red deer, staring buffalo, may already be mid-vote. What looks like nothing happening is very often a decision already underway. 6. Understand that swarm behavior, whether it's beautiful or devastating, runs on the exact same underlying mechanism. Positive feedback doesn't care if the outcome is a gorgeous murmuration or an agricultural catastrophe. Respect the mechanism regardless of the outcome it happens to produce. 7. Never assume chaos where there's actually distributed order. What looks panicked and random to you is, from the inside, one of the fastest information processing systems ever evolved. You're not smarter than it just because you can't see the logic. I never got to enjoy the ordinary parts of my life after that crossing. The boring Tuesdays, the bad coffee, the traffic jams that it turns out run on the exact same panicked driver math as a wildebeest stampede. So if there's one thing I'd actually ask of you, it's this. Go appreciate the mundane stuff. Go sit in traffic and think about how, technically, you're part of a leaderless herd too, just with worse instincts and significantly more honking. Nature figured out how to run flawless group intelligence with zero management, zero meetings, and zero corporate email chains. Meanwhile, humans invented the reply all button. We really did not deserve the advantage evolution gave us. Anyway, I've got about 600 more migrations to watch apparently, so I should get back to it. Thanks for hanging out with the funniest dead person in the savannah. I'm assuming the title's mine since the competition mostly just moans and rattles chains, and frankly, that's just